Here we're going to practice calculating molecular weights and formula weights. Now we use these for the same purpose, and so the terminology molecular weight and formula weight isn't extremely important, but molecular weight refers to the mass of a molecule, either in atomic mass units or the mass in grams of 1 mole of that molecule. It would give you the same value. Formula weight is the same idea, except it's the mass of 1 formula unit of an ionic compound. And so what you see here on the left are some models of molecules, carbon monoxide, carbon dioxide, sulfur dioxide, etc. And on the right are some images of some ionic crystal lattices. And so you would use molecular weights for the items on the left, and you would use formula weights for the compounds on the right. Okay. Now, what you call it is a little bit, it's just kind of a semantics sort of issue. We're going to use these for the same purpose. So I wouldn't get too hung up about the difference between molecular weight and formula weight, but that's how you know which one is which. So we're going to start by calculating the molecular weights and formula weights of the compounds that are shown here as models. We're going to start with carbon monoxide. Carbon is here, 12.01 is, and then oxygen is here, 16. So the molecular weight of carbon monoxide is 12.01 plus 16.00, which gives me 28.01. The units are either atomic mass units or grams per mole. They are the same. So here you have either unit is fine. Now in terms of significant figures, most of the elements, most of the atomic masses on the table are accurate to the second decimal or the hundredths place. That's not always true, but the two here are definitely accurate to the hundredths place. Because you're just adding numbers together, then you're gonna have you're gonna round it to the hundredths place. Now let's do CO2. 12.01 plus 2 times 16.00 is going to give me 44.01 grams per mole. And here I'm underlining the least significant digit, hundredths place, and that's why my answer is rounded to the hundredths place. SO2, if we go back to the periodic table, sulfur is here, 32.07. So we're going to do 32.07 plus 2 times 16 gives me 64.07 grams per mole, or AMU. Again, accurate to the hundredths place, 2 digits after the decimal. That's the addition-subtraction rule. In a molecular weight and a formula weight, you're just adding a whole bunch of numbers together, so it's always just addition that you care about. Even though we're multiplying 2 times 16 here, you're really just adding 2 16s together, right? I'm just trying to simplify it mathematically. But it's always just a bunch of addition and subtraction. Addition. SO3 is 32.07 plus 3 times 16, which gives me 80.07 grams per mole. SF4 is next. We have to look up fluorine. Sulfur is 32.07 and fluorine is 19.00. So you get 32.07 plus 4 times 19 gives me 108.07. Now this is a point where you probably would have rounded this to 4 sig figs, but remember that it's the addition-subtraction rule. So it's not the total number of sig figs that matters, it's the place. So just because you add a hundredths place, that does add a significant digit, but that's okay. Addition and subtraction rule says that it's accurate to the nearest place, right? The least accurate place, which is the hundredths place. You're going to keep all 5 of these sig figs. Now we're going to do C60. C60 is an allotrope of carbon called Buckminster fullerene, right? It forms this geodesic dome structure, and the reason it's named Buckminster fullerene is because he was the architect that originally designed the geodesic dome. So the men who discovered C60 named it after him. Now this is going to be 60 times 12.01. And you end up getting a really big number, 720.60 grams per mole. It's accurate to the hundredths place again, even though it has 5 sig figs. Now we're going to move on to sodium chloride, the formula unit for sodium chloride. If we look up sodium, that's number 11. It's 22.99 gram AMU over here, and chlorine is 35.45. So we add those together and we get 58.44 grams per mole. And we'll circle that. Accurate to the hundredths place again. Calcium chloride, calcium is here. I'm sorry, calcium carbonate. Calcium, carbon, and oxygen are all here. So add these together. Calcium's molecular atomic mass is 40.08. Carbon's is 12.01. And then remember that the 3 goes with the oxygen. 3 times 16 is 100.09 grams per mole. Now we're going to move on. We're going to do the ones inside the box. We're going to calculate the molecular weight of glucose. Glucose is a molecule, so it's going to be a molecular weight. The formula weight is going to be for the two ionic compounds. This is just showing you that molecular weights refer to the molecules and formula weights refer to the ionic solids. And this is to show you that if we take the entire sodium chloride lattice that you see here, this big giant cube of sodium chloride ions, that if I'm putting a circle, I'm encircling the single formula unit, which would be 1 sodium and 1 chloride. And there's another formula unit there, and there's another formula unit there, and there's another formula unit there. So I've circled 4 formula units. The actual numbers vary with the sample, but the ratio is always 1 to 1. Now if we look at calcium carbonate's formula units, there's 1 here. So the calcium is shown with the green sphere. Carbonate is this black carbon with the 3 oxygens attached. So carbonate is a polyatomic ion, which means that the oxygens are covalently bonded to the carbon, but they have an overall charge of -2. And then the calcium has a +2 charge, and so that sticks to the carbonate in an electrostatic positive-negative attraction, right? An ionic bond. So that's 1 formula unit for calcium carbonate. There's another formula unit there. And I've highlighted the calcium's the green and the carbon is black and the oxygens are red. So calcium in green, carbonate in black and red. So that's 1 formula unit for FU. That's funny. Anyway, so glucose is a molecular weight because it's a molecule. So we're going to do 6 times carbon, which is 12.01, 12 times hydrogen, which is 1.008, and 6 times 16, which is oxygen's atomic mass, and that gives me 180.156. Now this is the first time that I've actually gotten an extra significant figure that I need to round away, okay? So, and the reason I got that extra significant figure is because the hydrogen atomic mass it usually has 1 extra digit at the end. It's accurate to the thousandths place. But the other 2 are only accurate to the hundredths place. So we have to round this to the hundredths place. And so that means we need to round it. We need to round that 5 up to a 6. 180.16 grams per mole or AMU. Part B, magnesium phosphate. This is a formula weight that we're going to do. Magnesium is here, 24.31. Phosphorus, 30.97. And oxygen is 16. So we're going to add these up. Now I want to make sure everybody understands. We do 3 times magnesium. That should make sense. But the parentheses go with, the 2 here around the parentheses goes with phosphorus and with oxygen. So it's 2 times phosphorus and it's 2 times 4, 8 times oxygen, right? Make sure that makes sense to you because we have 2 phosphates. We therefore have 2 phosphorus atoms and 8 oxygen atoms for every 1 formula unit. And if this is confusing to you, go back to calcium carbonate and see that each formula unit for calcium carbonate contains 1 calcium, 1 oxygen, and 3 carbons. 3 oxygens. 1 calcium, 1 carbon, and 3 oxygens. Just like here, 1 formula unit for your magnesium phosphate contains 3 magnesiums, 2 phosphorus atoms, and 8 oxygen atoms because it has 2 phosphates, right? So make sure that makes sense to you. And then when you get 262.87, accurate to the hundredths place. Part C is going to be another formula weight because that is an ionic compound, sodium sulfate. So formula weight for this, we have sodium, sulfur, oxygen. And then this is a hydrate, so we also need water, H2O. So the formula weight here, we have 2 times 22.99, that's sodium. Sulfur, there's 1 sulfur, 32.07. There's 4 oxygens, that's shown here, 4 times 16. Plus we have to add in, there's 10 water molecules. that are sort of incorporated into the crystal lattice. And so we don't have any pictures of hydrates here to the right, but if we did, we would see that for each formula unit of the ionic solid, there's going to be some number of water molecules associated with it. And so in this case, this is called a decahydrate. Deca means 10. So that means every time this crystal forms and this ionic solid crystallizes, each formula unit of sodium sulfate contains 10 water molecules as well. Now we talk a little bit about hydrates in class. You can do a lab with cobalt chloride hydrate, right? So we're going to do 10 times, this is the molecular weight of water, which I obtained this way. 16 is oxygen plus 2 times hydrogen is water's molecular weight. And I'm going to add all that up, and that's going to give me 322.21 grams per mole, which is the answer here. Now hydrate, I'm just trying to circle this to make sure everybody understands, that goes into the formula. So hydrates always have some integer number of water molecules associated with each formula unit of the ionic solid. And the name usually includes that. So here decahydrate has 10 water molecules. There's also monohydrates and dihydrates and trihydrates, et cetera, et cetera, et cetera. So you can have any number of water molecules associated with a given ionic solid, and different ionic solids form different kinds of hydrates. They're sort of common hydrates that form.